Okay, so the next topic we're going to talk about is quantitative variables. So, talked about categorical variables in the last one. Quantitative variables are slightly different. We're going to talk about what a quantitative variable is, what's the different aspects of quantitative variables, how do we display quantitative variables, how do we describe the shape of quantitative variables, and how do we describe the center. Okay, so what's a quantitative variable? A quantitative variable is any variable where an operation can take place on them, such as adding, subtracting, multiplying, and division, etc. For the statistics portion of this, we're probably going to use basically stick to averages. How can we tell the difference between categorical and quantitative variables? And it can be hard because the same type of variable, or rather, the same variable name can be different depending on what situation is, and that's what it really is, just looking at the situation itself. Actually, that light's a little bit too much for this, so we'll just go back to this. Okay, so how can we tell the difference between categorical and quantitative variables? It's got to determine whether or not it's being placed in different groups, or if there are just numerical data. It can definitely be hard to tell sometimes, but as long as you're doing some kind of calculation on your variable that's quantitative, and if it puts into a category, that would be categorical. For instance, look at age groups. If we calculate average age, that's quantitative. If we want groups of age like 10 to 20, that's categorical. So it's all based on whether or not you're actually taking an average, or you're doing some kind of operation, or you're sorting them into groups. Okay. So, how do we display quantitative variables? Frequency charts, histograms, stem and leaf graphs. There's also things called dot plots, and there's probably other stuff too. I mean, we don't have to go over them again. If you want me to go over things like dot graphs and stuff, I can do another separate video on that at some point, but it's not necessary for the class I'm teaching. So, what is a frequency chart? Frequency chart is a t-table where one side is labeled with the name of the data group and the other side is the frequency, which is a count of the data points. Each group of data must have the same length, which can't be the length of one. And I only put that in there just because I would have students who would put down like 12 and then they count all the 12s, and 13 they put all the 13s. You don't do that because it's not really a length there. You can't really, when you see what we do with histograms, it's really hard to draw a bar for a length that consists of only one number of 12. We must cover all the data points, and all groups must have the same length, even if the group length goes past the end of the data. We're going to make a frequency chart. Now, normally in a real-life frequency chart, you can choose any length that you want. I'm going to stick to a certain length just because I think it's helpful. So what I'm going to do here is this. I'm going to create a t-chart. Just like this. It says height of students in a particular high school, so we're going to put height here. And I'm just going to put the frequency over here. My neighbors are moving around upstairs. Okay, so I'm going to start at 50. Now that's not the lowest point up there. You'll see what I'm going to do. I like a certain thing because it kind of I think it flows better. But starting at 50, I'm going to go length of 5. So it's 50, 51, 52, 53, 54. So basically 5 integers. And then my next one is going to be 55, and then another 5 integers takes me to 59. And the reason why I like this one is then when I jump to the next one, it's real easy to know where I'm going, even though it wouldn't be too hard to calculate something else. I think this is the easiest one. Alright, I don't have to go any further because my highest point up there in that group of data is 72. And so 74 would cover it. Okay, so now what I'm going to do for my frequency is I'm literally going to count how many points fall into 50 to 54. So that's 54, 54, 54, 53, and that's it. So that would give me a grand total of 4 points. Okay, and then for every group, I'm going to count which ones fall into that range. So 55 to 59, I got 59, 56, 56, 55, 57, 58, 57, 58. I think that's it. It looks like it's it. Okay. 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 points. Okay, from 60 to 64. Adjust this. That's good enough. Okay, so 61, 2, 3, 4, 5, 6, 7. Wait, no, it's not 1. Yeah, 7 it looks like. Okay. 65 to 69. 1, 2, 3, 4, and 5. So that gives me 5 there, and then 70 to 74 looks like 1, 2, 3, 4, 5, and 6. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 28, 29, 30. So there's 30 here. If I add these up, there should be 30. So 4 plus 8 is 12. 12 plus 7 is 19. 19 plus 5 is 24. 24 plus 6 is 30. So that frequency chart is good, and that's all I need to do. That's all it is that's all the frequency chart is. Just put them in groups and then determining how many are in each group. Now, you didn't necessarily have to go by this set itself. You could have done 50 to 53. But then you'd have to readjust everything so it would be the exact same length. So like 50 and 53 would be 4 integers. So you'd have to make everything 4 integers starting with when you do 54. So that's completely up to you. But I like this one again because it's pretty concise and it goes by pretty easily because they just reset the pattern the whole entire time. What is histogram? Histogram is a way to graph the information from a frequency chart so that you need to create one in order to create a histogram. Luckily, we just created one, so we're good. It's like a bar graph. The difference is that the x-axis must have a scale on the bars. Each have a defined length. So it's very close to being a bar graph. If you watched my last video, this does look like a bar graph. The biggest difference is this. On the bar graph, it didn't have a scale on the x-axis. It just had it on the y-axis. You need the scale because you need to make the bars the same length in this case, which will come directly from the groups that you create, and you'll see that in 1 second. Both axes are still labeled, and we're going to create a histogram on the information that we previously had. Okay, so let me get my notebook here. Okay, so we're going to use the frequency chart from the last one. So if you want to see that again, you can go ahead, it's right there. You can reverse back and see exactly where the numbers are coming from. But let's go ahead and draw my histogram. Okay, so let's see. My bottom axis is going to be my height. My x-axis, I should say. And my y-axis is going to be my frequency. Now my highest frequency is 8, so let's go 1, 2, 3, 4, 5, 6, 7, 8. And so I don't have to start at 0 for my x-axis, but I will start at 50. I think I will go, how many do I have? I've got 74. We'll go every 2. 52, 54, keep going. I may have been able to go every one, but I'm already locked into it, so we'll just stick this one out now. Okay, I'll go to 76, but I'm not going to need it because my highest one is 74. Okie doke. Now, I need my bars. My first group was 50 to 54. So what I'm going to do is make my endpoints at 50 and 54. And that's going to be my bar. And my frequency goes to 4, so I'm going to go take this guy up to 4. Okay. Then my next one is 55, which is in between. Goes up to 8. $60. To 64, and it goes up to 7. Okay, 65 to 69, I believe. Yeah, 69 goes up to 5, and then 70 goes up to 6. Okay, so that's my histogram. Again, these are the lengths that we came up with, or the groups that we came up with before. That's why they're like that. That's why you have to have your scale at the bottom. Okay, that graph is going to come back up pretty soon, but for now, it's going to go away. The last way to show graph is stem and leaf plot. We have another T-chart where the title of the left side is the stem and the title of the right side is the leaf. The stem side is the common tens place of each data point. The leaf side is the ones place of each data point, listed one after another in order next to the tens place. Tens place can be duplicated. If a data point has more than 2 places, the extra numbers should be placed on the stem side. Multiple numbers must be placed if they exist. So we're going to create a histogram of this. So in order to do this, though, I need these to be in order from least to greatest. So that's the first thing I'm going to do is put all these points in from least to greatest. And so my smallest point is 54. I have 54 there, 54 there. Do I have any more 54s? I don't think so. The next one would be 55. 56. 56. Oh, I had a 53. Put that right in the very beginning. Right there. Okay. So 57. Why did I put 54? It's 57. Another 57. And I don't know why I draw sevens that way. I just saw it one time. I'm totally not British. But that's just the way it is. I do think it's nice though, because it differentiates the 7 from the 1. Let's see. Almost done now. Just to double check, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay. So now, let's create our old stem and leaf plot. So, after I put them all in order, I'm going to go ahead and draw another T-chart. Stem, leaf. My smallest one is 53, so I'm going to put a 5 there. And put a 3 there, and that represents 53. Now, I've seen it go back and forth. Some people don't put commas. Some people do. I'm going to put commas between all my numbers. And you need 4 4s, because there's 4 54s. So you don't just not write that. 55, 56, 56. Now, if you want to, theoretically, I could get this all on here before it ends. But just to show you guys, if you're running out of room, it's okay to drop another 5 down here, and just keep going. You don't have to if you feel like you've got enough room to go and finish off all the numbers with the 50s. That's up to you, but it is an option. 60, 61, 61, 62, 62, 63, 64, 65, 65. Let's drop another one right there. 67, 68, 69. 70, 70, 70, 71, 71, and 72. Okay, and that's my stem and leaf plot. Now, what happens if I want to display the number 103, because that's a 3-digit number? Well, technically I should throw an 8 and a 9 here, but when I get down here, I'm going to throw a 10. I'm not going to put the 0 over on the leaf side. The only thing that goes on the leaf side is the one's digits. Whoops, and that was a 103. I think in my head I was doing 102. So 103, there it is. So you always put everything else on the stem side. The leaf side just gets the ones digit. And that is a stem and leaf plot. Okay. So, whoops. grabbed one too many. So what are 3 aspects of quantitative variables? Well, shape, center, and spread. We won't talk about spread in this discussion. I have an entire topic about that all to itself because the spread's got a lot of bite to it. But we will talk about shape and center. Now, when we talk about shape, there is 2 main aspects of shape. They are symmetry and modality, or whether or not it's symmetric or not, and how many modes it has. So these are the 2 things that if I were to ask you what is the shape of this data, you would get back to me, oh, it's symmetric or not symmetric, but it also has this modality. Okay, what is symmetry? Just like symmetry in art, data can be symmetric as well. If you can draw a line down the middle and both sides of the graph are almost the same, it's symmetric. We say almost though, because data is not always perfectly symmetric. But as long as it's close to being symmetric, we consider it to be symmetric. What's close enough? Well, it's kind of a toss-up to what you think. But there are qualifications. It's got to be close to being the same thing on both sides. Like for instance, this one over here would be considered symmetric because I can draw a line down here, and even though this bar is slightly shorter than this bar, it's still considered symmetric because it's really close to looking like the same thing on both sides. Now, if it was super duper altered, you would not consider it symmetric. So use your own judgment, and this is where we get to things in statistics being a judgment call. So there's not always one right answer in statistics, which bothers a lot of people. It bothers me too as a math person. I like there to be one concrete answer. But statistics is very, very based off of justification, which is why 2 people can interpret a statistical piece of information differently. It's all in how you justify it. But symmetry, it has to be close to being symmetry. It does not have to be perfectly symmetric. Well, what does it look like if it's not symmetric? Well, it looks like something like this. When the graph isn't symmetric, what does it mean for the data to be skewed? Well, if the data isn't symmetric, then the data has to be skewed either to the right or to the left. That's your only 3 options. It's either symmetric, skewed to the right, or skewed to the left. A skewed data set would have a tail, which is a shallow part that looks like the tail of an animal. So if I were to draw currently some curves over top of this data, they clearly pull to one side. This is pulling to the right, this is pulling to the left. That's the tail of the data. The data is always skewed in the direction of the tail, hence if the tail is to the right, the data is skewed to the right, and if the tail is to the left, the data is skewed to the left. Well, you'll see it right up here. Here's the tail right here. It's pulling to the right, must be skewed to the right. Tail over here, it's pulling to the left, it must be skewed to the left. So, keep that in mind. You have 3 options: symmetric, skewed to the right, and skewed to the left. Now, what happens is this. We look at our original graph that we just drew. What conclusions can you come up with this? Now, in my class, when I did this, I've had people come up with 2 possible conclusions, and they can justify it on their own end. The first one is that this is close to being symmetric. One that I'm probably not in sharing of, but there has been arguments where these 2 are slightly off, and even though these 2 are a little more off than they should, they're only off by a frequency of 3. Therefore, it's close to being symmetric. Again, that's not my opinion, but one could make that justification that this is pretty close to being symmetric. I, on the other hand, float towards it being skewed to the left because it pulls over here to the left. It's very shallow over here towards the left. This one's a little bit harder. It's a little bit easier to see it when there's more bars. When there's only 5 bars, it's kind of hard to do skewedness and symmetry unless it's just right out there. But you can have justifications to either one. All right, so now what happens? Well, that's just shape. I mean, that's just symmetry. Of course it's shape. The other portion of shape is modality. The mode is what we're talking about in this case. So what is a mode? The mode is a set of data in the data pool. The mode in a set of data. See, I can't read today. The mode in a set of data is the data point that is repeated the most. So when you see a set of data and you see like 15, 15, 15 repeated like 8 times, that's the mode. In a graph, though, we don't always see the actual data behind it. So for us, when we see a graph, the mode can't refer to a singular point. It refers to the peaks of the graph. So essentially, when the graph pulls up and pulls back down. A graph is said to be unimodal if there is one significant peak in the graph. So like this one, it goes up and it goes back down. That's unimodal. It's bimodal when there's 2 significant peaks, up, down, up, down. So you got yourself a bimodal piece of graph. And then multimodal is when there's multiple ones. And then you also have this thing called uniform when there's really just nothing there. So that's your difference. It's basically how many times it goes up and it comes back down. All right. And notice how in the uniform graph, there are some small peaks, but they never really significantly rise or fall. So that's why it's not considered any kind of multimodal, because they're not really going up any high. It's got to be a significant rise. Now, once again, here's the data from before. What is this considered? In my opinion, this is unimodal because it rises up once. And even though there's a peak here, I don't consider it large enough, even though I drew it that way just to show you that there is a small peak there. I don't consider it large enough for it to be bimodal. However, some people do. You can justify it and say that that peak is large enough just because there's only 5 bars. And I may let you get away with that. But in my humble opinion, that's unimodal. But that's up to you. It's all in how you justify it. Okay, this graph is going away forever now. Okay. So that's shape. The last part of our discussion today is center. What does it mean for something to have a center? Well, we can look at one of 2 different things. Mean or median. Now, we'll define both of those real fast. The mean is the average. The median is the number right in the middle. So how does one find a mean? Well, the mean is just adding up all of the numbers in the middle. Sorry, not the numbers in the middle. Adding up all the numbers total. I'm sorry. I'm just looking for one paper that seems to be missing. But I'll have to write it out. Adds all the things in the middle. It's hit the middle again. Adds all the data points together. And then divides by the number of terms. So it's right there. We find the data by adding all the data points together and then divide it by the number of terms. The median is the middle number of the data, which means you must order the information from least to greatest. Note that if the middle of the term is odd, then the median is the middle number. If the number of the terms is even, then the median is the average of the 2 terms in the middle. Okay, so let's go ahead and take a look at this. So we will find the mean and median of both of these. Okay, so let me write these data points down real fast. 6, 8, 12, 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, good. And then the other one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. So, wait, is it binary? Oh, it is binary. Good. I thought it wasn't there. Okay. So, let's start by finding the mean. So the mean, I'm going to add all these together real fast. So I'm going to add all the numbers together. So 6 plus 8 plus 12 plus 11 plus 13 plus 14 plus 15 plus 16 plus 12 plus 14 plus 14 plus 15 plus 16 plus 17 plus 12 plus 18 plus 9. Okay, so that gives me a total of 222. Just double check to make sure I got all my numbers correctly. I sure do. Okay, so I'm going to divide now by number of terms, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So I'm going to divide by 17. And that's going to give me 13.0588. And that's my mean. Go down here, and I'll do the median in 1 second. We're going to do the mean for this guy down here too. So let's see. That's 5 plus 12 plus 13 plus 15 plus 16 plus 17 plus 19 plus 20 plus 23 plus 22 plus 21 plus 24 plus 3 plus 2 plus 5 plus 12 plus 11 plus 31. That gives me 271. Let's just make sure. 1, 2, 3, 4. Yep, looks good. So it's 271 divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 18. And I get 15.0556 is my mean. Okay. Keep it consistent, blue colon. Okay. So now we go back up here. Now I need to do my median. But to do my median, I gotta put everything in order from least to greatest. Oh joy. You'd think I would make this easier on myself. So 6, 8, 9, 11, 12, 12, 13, 14. Oh, there's another 12. Oh no. 12, 13. Why didn't anybody say anything? I know, because you guys can't talk to me. Jokes, they're bad. $15, $15, $16, $16, $17, $18, 1, 2, 3, 4. Oh, we're at 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, so 17 is an odd set. There should be one directly in the middle. So it should be 8, and then the actual median. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So just to count: 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that means my median is 14. Okay, and if we go down here, so 2 is my smallest one, then 3, so 2, 3, 5, 5, 11, 12, 12, 13, 15, 16, 17, 19, 20, 21, 22, 23, 24, 31. I wonder if I made everyone fall asleep because I was counting up like I was counting sheep. Who knows? Okay, so there's 18. So that means there's going to be 2 in the middle because it's an even set. That'll occur at 9 and 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that should be the natural halfway point. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so since it's between 2 numbers, I have to take the average of the 2, which would end up giving me 15.5. Okay, and that is my mean and my median. That's how I find them. Not too bad. The last thing I'm going to talk about real fast is a thing that's called resistance. And I want to show you exactly what it means to have resistance beforehand. We can have this thing called an outlier. I'm going to just throw a really obvious outlier here. I'm going to throw the number 105 in. So essentially, what I'm going to do is I'm going to go back to this original set, and I'm going to throw the number 105 in. Again, this wasn't in there originally, but we kind of want to see what's going to happen to the data if I throw this really extreme point away. Well, the median's easy because now it's an odd set, and now the median just becomes this. So the new median with new point is just 16. Okay, let's make a note of that real fast because it didn't really change that much. It only changed by 0.5, so it didn't change that much at all. The mean, though, well, we're going to take 271, which is the original total, and add 105 to it. And that gives me, let's see, 6, 7, 3. And then divided by, now it's 19, because we have 19 points, we added 1 point there. So 376 divided by 19 gives me 19.789.5. And you notice that that's a big, so this is my new mean, that's a big jump. Well, at least much bigger than the median. So what's happening here? It's this idea of resistance. So resistance and what it means to shape. Resistance refers to a piece of data's inability or lack of inability, because I didn't want to say the word ability for some reason, to move if data is added or subtracted, especially to extreme data points. Ignore the fact that I didn't put an S there. I'm not the greatest at English. I'm a math teacher. So, especially to extreme data points. So we want to look at each of these individually, and what we just saw was that the median is highly resistant. It doesn't change much no matter what points you put in there. It doesn't deviate. As you saw with my example, it didn't only deviate by 0.5, and really, in some cases, it doesn't even deviate by that. It's very highly resistant. The mean is weakly resistant, as it can change wildly based on what is added to the data. This is why you hear people all the time talk about how you can't use the mean, because if there exists, or at least especially when it comes to things like average income, because it'll fluctuate wildly if there exists several people on either end of the spectrum. This is also why if you are in a class and you get all A's on assignment, and then one time you get that one terrible C, and it drops your grade point average all the way down, because the average or the mean is very, very volatile when it comes to extreme data points. It always chases them. It's not a great thing, but it is what it is. So the mean will always go towards points that are far away from the data, and will always move towards the tail of the data. And we call those points really far away outliers. And we'll get into those a little bit later, but just note that that's the term. Outliers, data points are really, really far away from data. Now, it's to mention this is you want to know this because it actually helps you out with shape. Because you remember, the graph that I showed you could be interpreted in many different ways. Well, this can help you pin down how it should truly be, because these three rules always work. So if a mean is equal to a median or close to it, because remember, things aren't always perfectly symmetric, and again, that's going to be kind of your gut reaction to what it should be, but if the mean is equal to the median, it's symmetric. So if you have a mean that's close to a median, it's very symmetric. If the mean is greater than a median, though, and you have to be careful not to flip those around. So it's mean is greater than a median, not median is greater than a mean. A mean is greater than a median. The data is skewed to the right. If the mean is less than the median, the data is skewed to the left. And normally I would tell my students just to write it down so you can memorize it a little bit better. It's not necessarily, my students who are watching this should do that as well. If just some random person on YouTube is watching this, it's up to you. But these are firm rules that will work every single time, will help you determine whether or not the shape of the data is what you think it is. So for instance, if I go back up here, if I look at number 1, I've yet to actually create a histogram or a frequency chart for number 1, but without even looking at it, seeing that the mean is 13.0588 and the median is 14, and they're within less than 1, I'm thinking that the graph, or rather the histogram that I would draw, would be relatively close to being symmetric. If it's not, it's only slightly skewed to the left, but I'd be willing to bank that this is going to be a symmetric graph based off what I see. If it's less than one difference, then it's going to be symmetric. Unless the points are like really small decimals, in which case you can reevaluate that. But that's it. Let's see you in the next one, which will be about spread and box plots and all that good stuff.